Do you know who brought the concept of relativity for the first time? If you're thinking the answer is Einstein, then sorry, but you're wrong. The idea of relativity dates back to 1632, when Galileo for the first time put forward the principle of relativity, after which many others including Isaac Newton worked on this theory. Well, Galileo stated that it is impossible by any mechanical means to say whether you are staying at rest or you are moving. Now, putting this into a very simple language, you might have, while traveling in a train at least once in your lifetime, noticed the effect of relativity. So whenever you sit inside a train and look outside the window, you might have noticed some other trains passing by. Now, you might get confused whether is it your train which is moving or is it that one. This is relativity. Okay, let's take one more example. Now suppose you are sitting inside a car with a friend and the car is moving. Now you have one more friend of yours standing on the road observing you both. So there are two things here. Number one, when the friend sitting inside the car notices you, he would say that you are at rest. That means you are not moving. And when the friend outside the car on the road notices you both, she would say you are moving. Last example. Whenever you travel in a car and look outside the window at the trees, what do you notice? You feel as if it is not your car which is moving forwards, but the trees are rather rushing backwards, right? Okay, the three examples I showed you just now might seem a very common experience of daily life, but trust me, these are very crucial in understanding the concept of relativity. And I'll tell you why I'm saying so. So now let me begin with a technical explanation, and for that I will have to introduce you to some terms. The first one is an event. An event is something that happens at a particular position in space and a particular moment in time. Example, turning on a light bulb. It is an event which happens in three-dimensional space somewhere and also happens at a particular point in time. The next term is frame of reference. It basically involves a coordinate system from where an observer observes an event happening at some moment in time. So it has both the elements, time and space. Every observer carries his or her own frame of reference, and we assume that the observer is always sitting at the origin. Talking of the example I took earlier, in which you were sitting in a moving car with a friend, you sitting in a moving car was an event because it is happening somewhere in space and at some point in time. Your friend sitting in a car and standing on the road were both the observers, and the car and the road were the frames of reference of these observers. So typically, relativity is the study of objects in different states of rest or motion. It describes how the same thing may appear different to different people with different perspectives, or clearly speaking, with different frames of reference. So when you were observed by a friend inside the car, you appeared to be at rest, and when you were observed by a friend outside the car, so there is a change in frame of reference, you appear to be moving. And the reason we are studying relativity is that everything is in relative motion to every other thing. Now if you are thinking that you are sitting stationary watching this video, don't forget that you are sitting on Earth and Earth itself is moving around the Sun. Even the Sun isn't stationary, Sun is moving around the galaxy, and even the galaxy is moving. So everything is relatively moving with respect to other things. So the question is, what all changes when you change a frame of reference? Clearly, whenever you rotate or shift completely the coordinate system, the position of the event changes with respect to the observer who is sitting at the origin. But there is one thing here. Position or coordinates of a point in space may change due to change in frame of reference. But distance between 2 points, or rather I should call it length of an object, never changes, no matter what. Whenever or wherever you observe the length of a stick, it always remains the same. The next thing that does change with frame of reference is speed or velocity of an object. Now in the car example, when you were sitting inside the car, the inside observer saw you at rest, which means your velocity with respect to inside observer was 0. while for the outside observer, your velocity was something which could be measured. Also, if you are in relative motion with respect to the observer, which means your frame of reference is moving with respect to the observer, then in that case, the speed of object also changes with respect to your own speed. So for example, if a car is moving in the forward direction with a speed 80 km per hour and you are also moving in the forward direction with speed 30 km per hour, then with respect to you, the speed of the car would be 80 minus 30 equals 50 km per hour. Now consider another situation where both the speeds of the objects are the same as previous situation, but this time you both are moving in the opposite direction. So in that case, the speed of the car with respect to you would be 80 plus 30 equals 110. And I think this is quite intuitive because you might have noticed this effect while traveling on a road. You might have seen that the car was moving away from you faster than it should be. Okay, next thing is time. Does time vary with change in frame of reference or with relative motion? Does a clock tick faster or slower when it is in motion? I think the answer is no. In relativity, the things which do not change with change in frame of reference are called absolute quantities, and the quantities which do change with frame of reference are called variant quantities. So from our discussion, it should be clear that velocity and position of an object are variant quantities and time and length are invariant. That means they are absolute. Talking of the last example, whenever you are traveling in a car, you know that your car is moving forward, but it seems as if you are stationary and the trees are rushing backwards. Now this is a very important conclusion of relativity which suggests that no frame of reference is special. Even the trees can say that they were stationary and your car was moving. Now, no frame of reference is preferred in relativity. Both the conclusions are correct, which means when you say that it was I which was stationary and the trees were moving backwards, you are correct. And when the trees say that they were stationary and you were moving, they are also correct. Now finally, coming back to Galileo's statement, it is impossible by any mechanical means to say whether you are staying at rest or you are in motion. So what does this really mean? Okay, now listen to this very carefully. Whether you are staying in a frame of reference which is at rest, like a ground, or you are staying in a frame of reference which is moving with a constant velocity, like a car, any experiment you perform cannot make a difference between both the frame of reference. Which means that all the laws of physics remain the same in both the frames of reference. There is no experiment which you could perform to distinguish between both because the results would be the same for both the frames. Alright, so this was the basic idea behind the principle of relativity. Now of course Galilean relativity or Newtonian relativity if you like failed, because that is why Einstein came up with his special theory of relativity in 1905 and also general theory of relativity in 1950. So why do you think that Galilean relativity failed? After all, it is so intuitive and we do experience all such phenomena in our daily life, right? What's wrong with it then? Well, I'll leave you with this question for now until I am back, and in the next video I will be discussing why Galilean relativity failed and how did this mark the beginning of special theory of relativity. Until then, keep stargazing.